7 and 8 do.
I haven't decided on that because I got them all lumped up, right?
Yeah.
You guys, how long you think you want on them? Or these are getting a little more, but they're all power amps,
Yeah.
right? I don't know. We could go for, would next week be feasible?
Yeah,
Sure.
you could set them off for Monday.
You want to do them on, set them for Monday, give you the weekend to do them and stuff?
Yeah, that'd be
I
great.
mean, the nice thing is, in a simulator, it's a fairly, I don't want to say easy setup, but it is a fairly easier setup, if you will. Let's see, check. How about May 15th? Yeah, well, we could do that. But you know what the problem ends up being? When I do these open-ended labs, some of us, and I get it, some of us are procrastinators and put it off till the very last minute. And if I wasn't having to grade them all and everything, I wouldn't have no problem with that. But there's nothing like, and I mean, if you need more time, you know me, I'm always easy. I get it. Life gets in the way of things. Need extensions for stuff, same with the homeworks, same with the quizzes. If we need to push due dates back or anything like that, definitely let me know. My main thing is for you to be understanding this stuff, right? Not so much browbeating you with it. No, Aaron's kidding me. Okay, I get it. But no, we can do next Monday or next Wednesday, whichever you guys prefer. I tell you what, I'll set them for the due date for next Wednesday, and then if you decide, get them in earlier, that's fine. If not, and then I've been toying with this idea. I had a professor who never had a solid due date for his assignments, but he did have a set time, but he allowed you to always bring them in late, but with a point reduction, which I thought was always interesting. So you could, like, even if you get a solid A on, like, say, this assignment, but you turned it in like 2 weeks later, something like that, he would drop your assignment grade by a letter grade. So if you were turning it in, you got an A instead of an A, you would get a B. And I always thought that was fair, just because otherwise you got, a flat 0F, and that was never good. Because when I was in school, just like you guys, well, most of you guys, I had 2 jobs actually, and full-time school. It was fantastic. I worked. I actually worked at school when I was in there for Monday through Friday. I worked from 7 to 1, and then I went to classes from 1 to 7. That was my Monday through Friday, and then I had electrician job I did for Daniel's Electric in Chicago on the weekends, Saturday and Sunday. The only days I ever got off were like the holidays from school, or like, in between spring break and all that kind of stuff. And that was fantastic then. But for about 3 months every shot, yeah, I was going 7 days a week. So I get it. I know you fall behind. It's a killer because you literally have no free time to catch up with this crap. But so yeah, I almost want to redo the lab 5 questions, to be honest with you, Ben. I mean, really, the only truly relevant one is the very first question, because you really can't go back through on a chart. That's not.
I submitted it, and I tried to give it full effort, but
Yeah, no, I know everybody did. So I'm gonna go. Of course, those aren't gonna count against you. We'll go through and get full credit. My big thing is going through and understanding how this getting the formula down, right? The 20 log of AB, 10 log, and all that. Why we're doing it? Because we're going to start. I mean, basically every amplifier, you do have to go through and figure out what your response is for it, whether it's from a power end, or we're looking at from a voltage end, or even in the current end, and just understanding it's always fantastic. Yeah, we're always looking at output versus input to give us what our overall gain is, right? So even like the power ones, we're interested in, okay, what's my power out, and then basically figuring out the efficiency, right? But we're still figuring out a gain. Excuse me. So with all of these, and that's something that's going to stay with us, especially even when we go into op amps, we will still be figuring out very much a game. Let me switch my screen here. And this is, and this actually leads us up. And this better work today, I swear. I rebooted my computer. I don't understand why it wouldn't let me share that day. You guys all see that?
Yeah.
Fantastic. So now, so we looked at the small signal amplifiers, right? And so we've seen that we can indeed, and in fact, we can even bunch them up a little and have one amplifier, one small signal, one feed another small signal one until we get to a point where essentially the distortion effect is too much and that we can no longer amplify it anymore. And then we looked at the one where we had the cascade, right, where it had the unity gain feature to it, where we could take that noisy output, filter it through like a unity gains. Oh, good Lord. There. I think I got you in now, right, Brenna? Maybe. Sorry.
Back. Unfortunately, I have to share my server with my idiot father-in-law who likes to disconnect things and then plug them back in and think they work okay.
Oh, yeah, my brother-in-law does that kind of stuff to my nephew at home. My nephew likes playing, online games with his guild and all that. And yeah, my brother-in-law, if he's not liking the speed, he'll just simply pull out he pulls the power out and plugs it back in to reboot the router and stuff like that, right?
Oh no, he's not smart enough to do that. He's been doing work on his bathroom next door, and the Wi-Fi is actually in the room next to it, and he tends to flick off circuit breakers and then not plug that back in. So
yeah, awesome.
Sometimes I'm out internet for several hours before he realizes what he's done. That's what happens.
Well, that's even better than my brother-in-law, huh?
It's not malicious, just incompetent.
Oh, that's funny. Sorry. Anyway, so yeah, I mean, in the scheme of things, and then now we're going to start looking. Through chapter 37 and right, and looking at the power amplifiers, we're realizing that we could boost the hell out of these guys and what we're doing with those. And of course, certain ones have their drawbacks, right? So we have to we're looking at the efficiency. It's like, what are we getting out of these things? And then, and that kind of brings us full circle as far as like what we can do with transistor amplifiers, okay? Or amplifiers based on like single or double transistors, if you will. So then before we get into op amps, what I wanted to look at, and Frenzel's book he sort of covers this, but not in a way that beneficial. I don't want to get too down on the textbook, but anyway. So I wanted to look at something they call the differential amplifier. And we think of it like in a mathematical point of view, the differential, well, and I'll show you when we go through these circuits here of what that means. It's essentially you'll have two voltages that literally we take the difference of. One will literally be minus the other, and we take the remainder. And hence the term differential amplifier. Nothing hidden or anything like that. It is exactly what it says it is. And so we kind of want to look at the DC analysis of how this thing works and the AC analysis. I hope everybody's comfortable enough at this point that we can look at these, look at the way they do the input with these things. And then we're going to get into something, and kind of a new concept, which will go with us into op amps, is something they call common mode. And in this case, common mode gain, and we'll also be looking at something they call the common mode, the CMRR, which is the common mode rejection ratio. And it's something they call current mirroring, and looking at the loaded differential, different flavors of the differential, what we can do with it. And you'll be happy to know one thing: we have no bypass capacitors on the outputs and stuff, so we won't be dealing with those. So we won't have this what they call the low corner frequency. Now notice, you might remember, I don't know if I've gone through this, when we did the swamp CE, how the final output was like severely clipped, and even to the point that we had a little side clipping to the input, to the sine wave, if you will. So we won't be experiencing anything, you know, as far as what our response is to the circuit. So no low corner frequencies. Okay. And then we can do some interesting stuff with this thing. We're allowed, and depending on what we want, we can invert, we can not invert, or we can take the difference of our inputs, depending on what our goal is. So we can have our output be just one thing, you know, one single output. We can have it be a difference of two outputs, as I'm getting to show you here. And there's some unique things with differential amplifier, and this kind of sets us up for the op amp. So, and this is what I was talking before about something like virtual ground, where in this case, like, see how it says here that we have a high Z differential input, and the impedance is so high that it literally could be treated as like a ground point. Like in comparison, so if we're dealing with a high impedance, and I'm talking in the meg ranges, okay, it's really, really high. So it can almost, like I say, it can almost be treated as like a ground, if you will. And with these, with the differential amplifier, essentially it leads us into the op amp, and of course we have a high gain factor with op amps, depending on our configuration, and a low impedance output. So let's take a look at this, right? So here's a very classic setup for a differential amplifier. Now you notice we have the two transistors, right? And both have an input on the base, okay? And then they're coupled. The common, you know, our collectors are coupled and our emitters are coupled. But notice where we take our output in this case. So we have our VC1 and a VC2. And like it was referring to, we could take both of these outputs and use them, you know, as basically opposing each other. We could literally use one versus the other. And of course, the plus sign one would be the non-inverted side, and then the minus sign one would be considered the inverted side. So depending on what I wanted to do with my signal, that's how I would take our output. But the formula remains the same, whether you choose to use it, ground it out, or whatever. So if you ground it out, right, let's say in this case we grounded VC1, of course, then it's going to be what, 0. So when we subtract VC2 from VC1, it would be that minus 0, and that would be, you know, our V out is VC2, and vice versa, depending on how we want to use it. And again, we do you know, keeping our distortion factor, see how we use both BCC and VEE in this case, right? Remember, are always you're putting a negative because of our biasing our transistors, and VCC is our positive, and again, working with the transistors. So and there's one where we have a single-ended output, and in this case we use the one side, and like I say, the formula remains the same. It's just now you don't have the minus one. So we're basically taking a non-inverted output in this case. So when we try to figure out what our AV is, we have to basically use both, see how we use both sources in this case. So we do have V1 and we do have V2, because the way we figure out gain is still output over input. And that's all this is. He just juggled it around, right? So we figure, okay, our voltage out is equal to the gain factor multiplied by the difference between both sources, or both inputs, if you will, here, okay? And then this triangle symbol, now that's something, and we've been seeing that before, and basically that just covers the overall circuit, right? Well, when we get into operational amplifiers, this is pretty much the only symbol you're going to see. This is how they delineate or set up what the operational amplifier is going to be. And there's going to actually be a couple of ends to this and whatnot, but we'll get into that in a little bit. That'll be next week's fun. So yeah, and so the final, if we use the single-ended, right? So the final, of course, we're just using what the V1 in this case, because we do have, notice how the bass on Q2 is grounded. And we get to juggle with this thing a little bit. So depending on what our desired output is, we can manipulate this thing in quite a few different ways. It's kind of weird and it's kind of unique. And see, and this flips it around to the other side. Now we have no V1 in this case. We've grounded that out, and now we just have a V2 source, right? And of course, notice we always are still DC biasing these things. And that's the thing that you're going to run into, right? So eventually, what they ended up making from like this style and that, we went into integrated circuits, right? And one thing that you may notice on integrated circuits is we always have like a voltage in and a ground pin, right, to energize the IC. Well, that works for analog ICs and that works for digital ICs, and both, both respect. You literally have to turn these things on. And believe it or not, all these ICs are all basically just different manipulations of transistors. Even in the digital end, if we went through and looked at how they had it set up, well, they have these transistors all gated in different ways to give them their desired outputs. So we're still going through and having to DC bias these things to turn them on. And that's why we always have the DC involved. If we didn't have that there, basically these transistors would never be on, and we could crank signals into it all day long and there's nothing going to happen. So if you ever wonder, why am I putting this DC voltage to these things? Well, that's why. You're literally activating or biasing the transistors, if you will. So depending on how we use this, will depend, and it gives us different outputs, right? So we can look at it as being inverting. Now, when we say inverting, we notice here we have a negative sign. So an inverted output is considered a negative, right? And a non-inverted is considered the positive. And notice how the symbol's drawn out where we have a plus or a minus. So on the plus side, you notice we're grounded, okay, if we interpret that as far as our circuit's concerned. So we don't have a non-inverted input. What we have is an inverted input. So we have the minus one going in. So when we have that, basically we're looking at a negative as far as, see how we have that? So our output voltage would be a minus AB multiplied by the source voltage in this case. So then when we have the final thing, what would we expect? Well, our V out is going to be a negative whatever value it is, right? Because we have no values for this. This is just for the formula's sake. And these would be our golden rules. And I'll go through and actually post up a little formula sheet, if you will. And I haven't decided, I might give like a small amount of questions, like a sort of pseudo homework, but it would have to come out of the Malvino chapter, which I did post for today. And I might go through and maybe give you guys like 15, 20 questions just to have you go through and get familiar with the differential amplifier, if you will. Because I want you to get, it's sort of like cushioning the blow before we jump into op amps, just to help you get used to these new concepts of like dealing with inverted or non-inverted inputs, if you will. But these would be like sort of the golden rules, dealing with the differential amplifier as far as what our inputs, outputs, what we can expect, and how we would manipulate the voltages. Okay. And of course, as far as looking at the biasing, right? We're still going to look at the DC analysis. And notice in this case, he goes first approximation. So, and what does that mean for us? If you remember, a first approximation, we're ignoring the effects that are what happens with the transistor. So in this case, we're not going to look at that 0.7 volt drop across the VBE here. And of course, and we're not going to look at the resistance factor of this as well, right? So we're basically, with first approximation, we're looking at it as ideal transistor mode, if you will. So with that, basically we go through and state, okay, an Ohm's law, right? So we look at, and you see where the current's drawn here. So we look at I total, our total current of this circuit would be equal to, in this case, our VEE over our IE. Pretty simple, right? And of course, the rules still follow where IE is equal to IC. And in this case, we would have what? IT divided by 2. And going through, and a little, and the very bottom one is a KVL manipulation, if you will, where we want to try to keep our knowns and unknowns down, and make it manipulable for us, something that we can solve. So in this case, we're going to solve for VC, and so we're going to take VCC minus our ICRC, which would be what? The voltage of this, right? The voltage VRC. And that would give us our final VC here. And it's just a straightforward, like I say, first two, it's like Ohm's law, your approximation where IE is equal to IC, and then KVL is the very bottom one, right? Nothing crazy fancy. So now we look at it with the second approximation thrown in there, where we do have the voltage drops across VBE here, right? Both 0.7s. And so now we actually plug that in. And again, it's just an Ohm's law configuration of what we have for VEE would be minus our VBE. And remember, we have two sides here. So see how they have it drawn out, like, right? There's two IEs in this case. So IE plus IE would equal IT. And that's how we come up with dividing by 2, essentially. And again, down to the bottom one, basically plugging in KVL. So yeah, I think for the homework ones, I could go through and put up like a little formula sheet for the differentials, just so we get used to manipulating how we're looking at this. Because I know it's going to be a little weird just because of the way we have the two transistor outputs tied together like that, if you will. And of course, always when you add in values, it's going to change things. I mean, this one he keeps nice and simple, right? And remember, this is DC analysis, so notice on both sides of the bases here that they're grounded out, because we're not looking at any AC response at all to this thing. So then we plug through and find out, okay, so what's our I total in this case, right? So we take the VEE minus the VBE response and divide that by the resistor value, and we come up with 2.86 milliamps, right, for our total current. That would be down in this leg here. And then figuring out, now, because we do have two separate IEs in this case, right, and both being equal, so we literally just divide the total current by 2 and come up with the 1.43 milliamps. And that would be on both sides there, right? And the same with this, go through and use the second approximation, plug through and find out. Now we're going to go through the very last one, which was the KVL equation, if you will, and find out what our VC is. So we just take the VCC, minus out our value here. And we know that since IE is equal to IC, we're going to go ahead and plug that current in. We already have the value of the resistor, and just subtract that from our VCC in this case, and come up with our VC voltage, right? So in this case, we had 10.71 subtracted from the almost 4.3 drop across the resistor right there. And so that would be where, and that's right at this point, right? And notice that's exactly where your V output would be considered. So now you look at the AC response. And so then we have to go through, we could throw back in, okay, now we got a sinusoidal being injected in there on the base, and we go, okay. And it just says this is a single-ended output. So we just have the one, and so it makes our, the way we can figure out the AC gain here is fairly simple then. So we're going to look at it. Remember, what's our prime? That's the resistance or reactance, if you will, of the transistor itself, right? And you can flip-flop through it, right? And then you can find out, okay, so what's my one for this side? What's my one for this side? You don't have to try to solve both at the same time. And just remember that your final output one would be the one subtracted from the other. And it's always the case, but if you have one side grounded out, that side's going to be 0. So it doesn't really make our gain formula really complicated. We just have to realize how these two transistors, I mean, are almost like opposing, if you will, right? And that's really all it is looking at going through these are different ways to tie in. It's like how we're going to use these outputs. If we use both, it's the difference. That's where the differential part comes in. If we use one versus the other, we just have to notice which one we're using. If we use the plus side, that would be considered the non-inverted. If we use the negative side, that would always be considered the inverted. And then that should help showing what's going on in these legs here. I mean, it's fairly simple that both emitters are going to couple in and form like a total across the sky, right? And we just look at basically how we're controlling the base of this individual circuit. So with the DC, we end up biasing both transistors and turning them on. And in this case, like on Q2 side, our base is going to be 0, right? And then we have an AC on this guy. And then we just plug through and use our formulas accordingly. So if we looked at it, okay, what's my total current in this case? We got a 14 volt input on BCC, minus out the 0.7 volt drop, right? And then looking at what our 7K resistor is here on the emitter, coming out with our I total. And then just dividing that in 2, right? And that splits in half, so we get to both sides. And we come up with almost a milliamp, but not quite, 950 micros, right? Is this making sense? Am I going too fast? Or is any concepts we need clear on this, or is that all good? Now you'll notice in this that we haven't really looked at beta, right? As far as like beta IB being equal to IC or anything like that. It seems like it's been fairly beta independent, if you will. But we do have to look at beta when we solve for our prime, don't we? Remember from our formula sheet thing before, it was, let me see if I can go through and show you. I mean, in this case, he's using it just as the approximate rule, basically grounding out the DC side, figuring out that we have the 25 millivolt, and then throwing in the current that's involved in there, right? So we say R prime E, which we'll be looking at what? The forward bias effect right through here, so what our impedance factor is. So if we had a 25 millivolt drop, then we go, oh, okay, well, let's look at that, boom, 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 plug it in. We know what IE is in this case. That would have been our only unknown, if you will. And as always, the R prime should always be a fairly low resistance value, because that is basically the internal impedance factor of what the transistors are, right? And so now we just juggle through and figure out what our what we have. Then we go through and figure out what our AB response is for this guy. And we can see we have an AB of 190, well, 0.1. So, excuse me. And really that's all this is just basically plugging in our formulas, figuring out what our unknowns are in this case, just walking through step by step. Start with our DC response, get all our unknowns in this case, right? Our IE, our IC, and whatnot, just like we do with the other amplifiers. And then going through and figuring out what our AC response is overall. And in this case, now we figure out that we do have, in this case, so look, we have a 10 millivolt input peak. And then as our output, because of our gain factor of 190.1, we can expect to get out almost 2 volts peak in this case from a 10 millivolt signal, which is a nice decent gain. And the interesting thing is you don't have the RC filter effect in this case. You literally have, see, as you're taking both of your outputs here, so you should totally, and like I say, you'll have either a non-inverted or the inverted output in this case, or the difference of the two. And that's what you would expect to see. But we still have gain factors to deal with as far as our transistor, how much gain we're going to be dealing with. And we just plug through and then doing the approximation rules. That's he kind of moves ahead in this one, and so we don't have all the examples. I could go through if you'd like and show you like the AC approximation of the differential amplifier, if you will. Draw out like a little circuit for it. And another thing that I also had a request for, and I don't know if everybody would find this beneficial or not, but I can go ahead and do it. Do we want practice problems?
Yeah.
I mean, would you guys like small signal amplifier practice problems, unity gain practice problems, and then power amplifier practice problems, and of course then leading up to probably a couple of differential amplifier practice problems before we get into operational amplifiers?
Yeah, I think they're helpful.
As long as they're not taken for a grade.
Huh?
As long as they're not taken for a grade.
Oh, now you're taking all my fun out of it. No, it would be yeah, it would just be practice problems, you know, like given I mean, of course you're going to have the answers already, right? But it would just be a matter of you have to figure out how the answers were obtained, if you will. So like if you had a final value for, let's say, like IE and that kind of thing, and then basically you'd be working backwards and going, okay, how did we get these answers type of thing? Or would you rather, well, you'd have to have the answers in one case. It's just more difficult for me on the Blackboard side to give practice problems like that. But no, there's totally a feature where the grade isn't taken into account at all. You know what I mean? So I could totally just set it up, and then it's just a matter of, it's like, you know, basically figures on Blackboard and then having a series of steps, kind of like that one quiz that I gave you guys in the last 8 weeks. Because I know I'm just stepping through these remotes, and I know sometimes just the way it's like boom, 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 really fast, because especially with this, where we're just juggling formulas around, but it's like, okay, how the hell did he get these outputs? I don't get it. But we could do practice problems for that. But, and with all of these, there's always, you know, specifics, and there's always a certain style of formulas. I mean, notice in this case, really, again, all we used was Ohm's law and KVL. We didn't do anything real fancy here. It's just the way we do it, right? Because you have to take everything into account. It's like, all right, walk it down the ladder here and let's see what we have. But, okay, so now I'll do that. And then, I don't know if I'll continue on in this case. I mean, because now it starts to look at basically input characteristics of an op amp. Now, I want everybody to understand that the differential amplifier and the way that it's used, like those the two inputs, like it is, that is basically was the lead-in for starting to make an op amp. They essentially started making these differential amplifiers, and then when we started doing ICs, right? And this is considered an analog IC. 555 timers an analog IC too, by the way. But that's what they did beforehand, and then it's real like, oh, look at what we can do with these things and get these high gain factors and whatnot. And it was much more stable, if you will. So they started making these out on chips, and that's when the basically the number one most used probably op amp out there is the 741. It's like basically semi-famous in the electronics world, if you will. So I'll be going through and posting up a spec sheet for the 741, right? And that is, like I say, it's the numero uno of op amps. It's kind of like the 2N3904 is the most commonly used BJT. Well, the 741 is probably the most commonly used op amp. Oh, I think my wife might be home. Awesome. But the rest of this actually starts looking at op amp effects of how we're looking at these things. I don't know if I want to continue pushing this into your heads right now. And everybody looks like they're troubled so far by all the aspects of the differential. But no, what I'd like to do is, if you will, I want to post like I said, about 15 maybe homework questions on the differential amplifier. It's not really laid out very well in the Frenzel text, but I think that it helps a lot without just jumping straight into op amps. It's like, here, this is a whole brand new thing that has its own rules. But I wanted to show you that it may have its own rules, but they still are tied on from transistors. It's just the way we manipulate the transistors in this case, you know, putting them in opposition like that. So up to this point, like in the cascade style, right? The cascade style, they aided each other, right? And the differential style, they're opposing each other. If you get anything out of that whole crazy lecture right there, is that fact that they are in opposition, especially as far as how we look at the outputs of these things. And that's kind of how we're going to be looking at operational amplifiers. And we have, you know, differentials. They also do with something, you know, we'll get into that. And there's inverting and non-inverting inputs to these op amps. And there's inverting and non-inverting setups to these op amps as well. And there's just, as far as the labs go for that, I think there's like 4 primary ones that I definitely want to do for op amps coming ahead here. But I might hold that until next Wednesday, start doing op amps, and then what we'll do is we'll spend a little more time on the differential amplifiers, and I can go through and post up all the golden rules up to this point, right? For all the transistors. Well, I think I do have the AC aspects up and everything, but I'll make sure I have everything up. And then all the golden rules for the differential amplifier, and then I'll set up we'll do a series of practice problems, if you will, if you guys would really like that. Is everybody in agreement? You all want practice problems? This is definitely, I'm not going to be like spinning my wheels and having like maybe 2 people in the whole class actually doing them.
Yes.
All right. All right. We'll do practice problems. I could do that. And then, and I might do, I'm trying to think here. I guess we have to have a chapter 37 quiz as well. Trying to decide when I want to post it. I got it. I just have to decide. It'll be like the last quiz, right? For chapter 34, we'll do that too. It'll be based on the chapter 37 homework, and then we'll just post it. Of course, take-home quiz, right? No. But is that clear? Does anybody have any questions on this so far? I mean, is there anything that's like majorly confusing you with these amplifiers? Did I not go over something well? Did you want me to go over something more? We can use, if you want to take more time, we can review some stuff if you will. We can even look at stuff on the simulator if you want. I throw it open to you guys. How's that? Let's see here. Oh, the heck. Now my chat roll here. Let me stop. We're going to stop sharing. We get yeses and yeses and yeses all across. Okay. I don't know. 3, 4, 5 yeses. I got a class of 18, I think. But, and I did mention, right, that they did come up with like a final determination decision as far as like the grading aspects for this class, where it's going to be the pass fail instead of the ABC.
The president sent out an email, and basically you can opt pass fail, but you still have the option to take your A, B, or C grade.
Oh, did they? No, see, I didn't get. Well, I'm glad you have that information.
Yeah, that's what I seen too.
So, oh, I see. So if you came out of the class with an A and you chose to go that route and get the credits for it, you could do that then, is what you're saying?
Yeah, the other thing she pointed out in the email is that if you're planning on transferring credits, pass-fail classes generally don't count, depending on the transfer agreement.
It would
So
be
it's
school
something to-
specific then, wouldn't it? Right, that makes sense.
Yeah.
Okay. Right, so yeah, if you planned on going to like IVCC or something, another community college, then you would have to probably repeat the class or something like that, huh? Interesting. All right. Well, that makes sense, I guess, kind of, sort of. But all right, well, good. Well, good. Now I haven't gotten that email actually yet. I have to go. Actually, I have to go through a bunch of things today with this class, but I'll post those up. I'll make sure I have all the questions for the next set of labs up. We'll do the practice problems. I'll try to, I don't know, it was like one example from each type of circuit be sufficient, or do you guys actually want a couple with different values to kind of play with? I'm easy. I mean, it's easier for me to set up than just having to go, well, in some respects, but I do have to make sure that they're balanced circuits. I just can't arbitrarily pick values and throw them out at you, you know. I mean, I could, but the circuit may or may not work in that case. So, but I could definitely do at least one of each style. So you'd have like 4 small signal amplifiers, if you will, and then we could look at I don't know, the 4 major classes of power amplifiers, and do the class A, the B, the AB, and the C, if you will. Anything after that, I think, is kind of redundant, just because they're so rare. I mean, there are other class amplifiers out there as far as power amplifiers go, but you won't see very many of them. These are basically the 4 majors. When you go out and look at ratings and stuff like that, these will be the types you see. Oh, all right, Nick's got to go. Hey, Nick. But I can do that, and then, yeah, I'll post we'll have the chapter 37 quiz. I'll make sure I have the lab questions posted up. I think these ones I'll double check, but these ones should all be relevant to the lab and the simulator. There might be a couple of, well, of course, there's always tables and charts to figure out, but these ones shouldn't be that bad. We don't have to deal with distortion factors so much. Now we're dealing with the power factors. And then I'd like to post up maybe 15 like homework questions, if you will, on the differential amplifiers. And I could even set up practice problems for that, because that would actually be beneficial. And just going into op amps and understanding these concepts, I think will help a lot. I just, like I said, I didn't really like the way Frenzel just literally jumped into op amps like he did without all this other stuff. So then what we're going to do is, after chapter 37 here, we'll bounce back and go to 34 and 35, and then we'll jump ahead and get into 38. I would like us at least to get into Frenzel's, past chapter 38, if you will, because he starts getting into oscillators, which is also important. And then basically we'll end it up or tie it up, if you will. Once you understand oscillators and all these other, we get used to the linear IC concept, then we can go and look at basically this class would end with the 555 timer and the interesting things we can do. Because you could set the 555 timer up for an oscillator, right? And so, which case, let's say you wanted to make like you wanted to use your amplifiers and you wanted to make like a siren effect, you know, like the fire engines do and that kind of thing. You could literally set the 555 timer up to oscillate and vary like that, so you would get different siren sounds coming out of a speaker, if you will. Okay. Make something like that, set it up at home and just power it up with like some DC batteries and scare your cat or something if you wanted to. No. But all right. So do we have any questions then? Does this seem fairly straightforward for you guys? Are we struggling really hard with these amps, or is this going okay?
No, going all right.
Yeah. It's kind of making sense. I mean, where our direction's headed and all that. Sorry. I just, like I say, this is my first time teaching these classes, and I do have, like I say, my direction, how I want to go with this at least, and what we want to get out of it. Like I say, we're just, we end with linear ICs, op amps, and timers really, and how we can play with stuff. I mean, we're not in the lab, so we're not going to be able to build like a radio, if you will, which would have been a little harder, but we could have definitely made like a transmitter and receiver type of thing, but we won't be able to do that. Oh, no. Gosh. Oh, good God. There we go. But yeah, no, so yeah, I'll go through all that today. I got a lot of, my cat's being a jerk. Yeah, if you give him that little siren thing, you can even make, well, I'd be pushing it a little bit, but we could even do one of those little, like, little cars, you know, with a little motor to it, and have it drive around with a little siren and, yeah, chase the cat. But yeah, this class will tie up your linear, and a little further on with the op amps, we're gonna start with linear, so it's all understandable, and then we get into something like non-linear applications, if you will, and how we use those. And that ties in. It's good for understanding like how regulated power supplies work. That helps with that. The radios and transmitters and that kind of thing. And then even down to the point where like even with stuff with the PLCs, as far as like the A to D converters and D to A converters, or even your like freak drives, you know, because on the freak drives you're using a lot of transistors and diodes with those, and essentially like amplifier style setups, and that's how they kind of play with you know, frequency variation, right? And that's how you're able to control your AC induction motor, which is the most widely used motor in the world. And if you're going to learn anything and how to control your AC induction motor, would be most beneficial for you, my young industrial electricians. But, and that's kind of what this goes into. You'll be able to understand the controls and stuff like that. And if you ever had to, you'd be able to even look at a freak drive and repair it if you actually absolutely wanted to. Because usually what ends up happening is the same thing that happens with the alternator of your car, where the diodes burn out. Because the same thing, you can even repair your own alternators on your car and save yourself a bundle of money, right? You get those little, and I swear to God, those diodes are really cheap. And then what do they charge you for what they call a rebuilt alternator? And it's like, it's not cheap, right? But yeah, it probably only costs you a couple of bucks to repair one, and you'd be able to do that. But that's all. I'm just rambling on. I got, but no, did you have anybody having anything you wanted me to go over, or we're good with this point up to now? I hear nothing.
I'm good.
I'm good, Tom.
All right. But yeah, that's how we're kind of going. And then, you know, but yeah, if you have any questions on this stuff, like I say, Lab 5, I apologize. I thought we had more control. And see, that other simulator I was looking at would have been able to do that, where we would have been able to actually define where that, our points on our Bodie plots and that kind of thing, so we could actually see the stuff and tabulate it, right? But with this one, we're just pretty much stuck with, you know, varying the values and watching the response of it. But I just wanted everybody to be able to at least look at that and recognize what they're seeing. It's like, yeah, your RC response. It's like, what's going on here? What kind of distortion can we handle? Because you will get into that with these amps. You know, you're always, like I said from earlier, you're always going to have a certain degree of distortion. There's no getting around it. It's just a matter of how much distortion you can deal with, right? And how to control it, balance it, and that type of thing. But every amplifier has its own little kind of job, and that's what it can do. Same with even like the power amps and, you know, with your music amplifiers and stuff. But yeah, you literally can go through and, I mean, the cool thing is literally fix this stuff for pennies, or, you know, even a couple of bucks. Like you said, with your power amp, where it's sounding a little funky. I swear to God, I would be willing. I'd give you my one pinky finger if I'm wrong. That if you go through and change out, and I swear, all those electrolytic capacitors on that thing, and, get yourself a little Weller, and they're pretty cheap. Actually, I was looking at that digital one that we bought for school. Believe it or not, is actually cheaper than the original style one with just the little knob controls. And I'm like, all right, go figure that. It's supply and demand, I guess. But yeah, it wasn't that expensive, and they work really nice. But yeah, you go through. Like I say, the biggest thing is always measure those caps and make sure you get the right size, because even 22 microfarads or any values, they always come in, you get the long, thin one, short and fat, and all kinds of different sizes, and it changes your lead lengths, where it'd be a royal pain in the ass. And then invest in a little silicone glue. In some of those cases, they'll have them tacked down, and that's what that is. It's just this, non-conducting glue. Be careful with that stuff, though. If you ever open, and here's this little repair thing for you guys. You ever open up, and this could be a DC supply at like some warehouse you work at or something like that, right? And these things stop working, and you open it up, and the glue that they use to tack it down has turned this like brownish color. What happens is, once that glue turns this brownish color, it becomes conductive. So what's happening to your electronics here is that the glue is shorting your crap out. So a real cheap, another cheap and easy fix, this even for home electronics, go through with like, those X-Acto knives, like the hobby knives, right? Go through with those real lightly across a circuit board and literally scrape all that old brown glue off, and then use that clear silicone glue and retack everything. If it's important that it be tacked down, otherwise don't even bother. But I swear to God, that if the glue, like a white or a clear, has turned like a darkish brownish color, it's basically oxidized to the point where it's literally gone through and become conductive, which is a crazy thing that nobody knows. But yeah, it's like cheap and easy little things you can do to fix your own stuff that would cost you hundreds of dollars. And it's like, no, they're ripping you off, people. But electrolytic caps and scrape glue, and these are real easy. And I swear to God, your power amp will probably sound like really awesome. And the only other thing to go through, and because you could check the forward biasing, right? Like let's say with like a diode. Well, it works the same way with the transistors, and go through and make sure that the legs there, the diode effect, if you will, between them all, where that it hasn't shorted out or it's blown, because that's how and it's real quick and easy. Just ohm it out in the one forward direction. And a lot of the handhelds these days have that little diode deal on it. Yeah, and you go through and just verify, from the spec sheet, make sure which way these transistors are oriented, right? And then just, boom, 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 down the line. And it's a real quick and easy, and you can verify, oh, well, this one transistor's gate is blown. And again, for a couple of bucks, go through and change that thing out. And the cool thing with those metal ones, 9 times out of 10, they're not soldered. They're literally, what they'll do is they'll put them on like a post, like a plug-in style, right? So when you undo that nut and bolt combination that they usually have, and you got to watch out, they'll sometimes have like a non-conducting film of some kind behind it. Don't lose that crap. But yeah, you could literally they'll pull right out of post, just like chips sort of on a socket. So it's sort of like a power amp transistor socket, if you will. But yeah, so those
like a tube socket almost is what it sounds like.
Yeah, and it's real easy then, because then you don't have to deal with desoldering it and resoldering it and that kind of crap. It's just post. And that's another thing too. Sometimes anything that goes into posts and sockets over time, that's another way to refresh your electronics. Sometimes that, those are on tension, right? So you get like a spring tension that's on that pin or that leg. Mm-hmm. And then over time, like you said, the things from the 80s, that spring, springs, right? So it starts to give out, and just replacing those little posts as another way to give it a facelift for real cheap.
Yeah.
Yeah, I've done that with a lot of, like I said, I used to do cat service tools like crazy, and And I don't know what it is with Caterpillar. You'd think this multi-billion-dollar corporation would revamp and stuff, but you get this crap where they got all these handhelds from the 80s and 90s, and they want them rebuilt. They don't want to buy new, and it's like, all right, let's go through and do it. Yeah, I know, crazy, right? The only thing that Cat Service Tools they do have a new like multi-programmable tool out that they sell now, which is utter crap. The thing sucks. But I didn't say that. That they've revamped their network topology, right? So they have like a new interface thing, which I do feel is they should invest in. Anybody, the old ones, the network topology is just it's insane to deal with. But these new ones are real nice and Wi-Fi capable and stuff. And you just plug all your stuff in line, and it'll still work with the old style stuff. That was one nice thing Caterpillar did do. But and the reason, yeah, they do keep the old tools versus this brand new digital one is the digital one, by comparison, it sucks. I didn't say that. I didn't talk bad about Caterpillar, right? Our school loves Caterpillar, but but that was the one thing I didn't understand. Otherwise, I was fairly impressed. They even do because you can go through. They get the vibration analyzer, and there would be one to learn what harmonics from, right? So what you'll do is you literally will go around a tractor, bulldozer, right, truck, whatever, and they've got for each one they've got you download these plans, and you'll go around with these little what they call an interferometer, which is like a thump sensor. You know, it basically is listening to like ping, bing, 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 bing kind of thing. And so what you do is you put these things on in different points, and what it'll do is it transmits a signal to it. And it literally listens to the bounce back. So here's your harmonics in effect, right? But it's looking for a fine tune. And believe it or not, it'll literally find structural integrity flaws. Like say the metal's got stressed. Yeah. Because good metal will bounce back a certain frequency, right? And if the metal's like stressed or stretched or cracked or something like that, especially cracked, right? It'll bounce back an entirely different frequency. And this instrument has you go through and like literally check all around the whole tractor whether or not you have any structural integrity problems. And yeah, it's what the hell did I just say it was? No, I can't remember. See, I'm getting old.
Interferometer?
Yeah, with the interferometer. So yeah, you're just going around with this thing, and it's got like a little wax. You get like this weird wax stuff, and just plaster it on a little bit like putty, and just plop, stick it right on these points. And you go through and measure, and it's like this digital handheld thing. And you just go through and measure all your different points, and it'll tell you if your tractor's still structurally sound or not, believe it or not. Yeah, Caterpillar makes some weird stuff if you ever can get into that. I've even had to do, they had like flow meters, you know, for how much gas. Oh my God, these things guzzle so much gas. It was insane. But they'll literally put these things in line to make sure that it's actually not guzzling too much gas, because they'll literally watch it while it's flowing through, you know, while it's being fed the gasoline in those big ass engines, and they'll monitor it. Yep, that's crazy there too. They got a little magnetic resonance deal that they deal with and measure the flow rates. It's real weird, but yeah, Cat Electronics was interesting. You ever get a chance to work for them? They don't hire very often, because usually once those guys get in Cat Electronics style, they're in for like life. Most of them are old farts, and I'm talking like old farts compared to me old farts. I was the youngest guy, believe it or not, and this was after I turned 50, and it was, and I was like the kid by comparison to all these old guys. But yeah, once you're in these Caterpillar service jobs, you're pretty much in there for life. And it didn't help. They moved their main electronics facility thing. They moved it up to Canada. I think it's in Toronto, actually. So if you ever wanted to work for like Cat Electronics and live in Canada, that would be an ideal opportunity. But anyway, but I digress. But yeah, as far as doing your own service for this stuff, you know, and that's one of the things from all of this, you know, especially like your amplifiers are starting to sound like crap or work like crap. it's really not that expensive or very difficult to go through and repair all this crap. I mean, I always do, unfortunately, and then I've stopped doing it for friends of friends and friends of friends because people all of a sudden will take crazy advantage of you. Oh, you know how to fix that? And the next thing you know, your wife has got you hooked up with like 6 million odd jobs. I'm like, all right, this is a little nuts. I'm gonna start charging people for this crap, but but doing it for like friends and family is usually all right, immediate family and friends. But yeah, I would definitely step through your power amp there, Sam, and I would, make it a little weekend project, if you will, and measure all your caps and buy some new ones. Those electrolytics are cheap, and if they had them, and I'll warn you guys, and this is a wonderful Asian little ripoff that they did from. And I'm not trying to talk down on the Asians. It was a really bad manufacturing practice they did from about 95 to 2005. If you have any electronics from that end and they literally have failed, and I'm talking refrigerators and all kinds of crap, they got busted doing this, but they were using really inferior materials on all their electrolytics, and they were prematurely failing, like badly. So all these name brands and stuff. So if you had a fridge that was like from that time and it just quit magically, and it's like, I've only had this fridge 3 years. It's like, oh yeah, because you got this Asian crap in there. Yeah, you get what you pay for. But they were literally using, and I'm talking with all of them, Nichicon and all those different Ichicons. There's like Nichicon and I can't remember all of them. But they all have some kind of econ kind of last name to it. I don't know why, but yeah, they were all using really inferior materials for all their electrolytic caps. But you can always, at the very minimal, expect 5 years of life out of an electrolytic, and these things were failing after like 2-3 years and making like Whirlpool and all those guys look like crap. It was like, what kind of crap are you guys pushing out here? And it's like, and they were scrambling and trying to figure it out. And it ended up coming back the weirdest, cheapest little piece. And yep, they were buying all from Asian manufacturers back then because they were cheap. And yeah, they were cheap, all right. But yeah, it was, I mean, it's hard to get electrolytics made in America or anything like that, but the Asians learned their lesson apparently from this. And so that now they're actually making good electrolytics. But yeah, you got to watch your parts. If it's cheap for a reason. And watch what you're getting into with some of these companies, because they don't have all the regulations and stuff that we do. They pretty much do whatever the hell they want, and who cares about copyrights and stuff. That's one of the flaws of doing business with them. I mean, the Japanese recognize a lot of our patents and copyrights, but a lot of the rest of them don't, and they don't even follow the rules when it comes to making this crap. So when you buy Asian parts, and especially you go in at like that Alibaba, yeah, take that stuff with a grain of salt, because you're literally getting what you're paying for. If you're paying crap, you're getting crap. I don't mean to, it's just the stuff I've run into in the last 20 years, and it's like, wow, So yeah, but no, try that findchips.com, and it looks at Mouser, DigiKey, Allied, and all the big like suppliers. It'll look at all of them, because not everybody carries everything, but it'll look at everybody, and even some weird warehouses in some cases, and spit stuff back at you and be like, oh, awesome, But I always highly recommend findchips.com. That's my little home hobbyist website, if you will. But no, it's easy to use too. But anyway, so now if you guys have no questions, that's kind of where we're going. We're going to be looking at the differential amplifier, tying up power amps and stuff. Yes.
So you're gonna make a new lab 5 for us to do, or do you just submit it and you'll pretty much just give us full credit for question 2 and 3?
I think I'm more along that lines. Let's just go through it, and then 6, 7, and 8 will be, yeah. I'm going to go through all of them today and make sure that I got all the questions how I want them and whatnot. But yeah, if you've submitted your screenshots and gone through, yeah, I'll give you full credit for those ones. It was just really getting used to what your RC circuit's doing, you know, like more of an applied, like, yeah, you learned it back in AC, but did you learn it? You know what I mean? And that's what it is. Just like basically being able to look through and going, oh, that's what they mean by frequency response. That's what we mean. And how the, 20 log of AB equates into that. So if we vary our amplitude on an RC, what is happening in this case, okay? But that was my primary goal with that. But yeah, if you submitted it, Jared, I'm all good. All right.